Hello, and welcome to the Calculus 1 playlist. This is the first video in a series of videos that go along with the OpenStax Calculus Volume 1 textbook. This is a free textbook that you can get online. Just Google OpenStax and open up the Calculus Volume 1 textbook. In this particular video, what we're going to do is we're going to talk about where calculus came from, where it started, what led to the development of calculus. You have to keep in mind, calculus was a massive, massive discovery. Without calculus, we'd probably still be riding horses. Calculus in many ways unlocked technology and engineering and allowed the Industrial Revolution to take place. So let's go ahead and get started. I'm going to share my screen with you. And remember, if you want access to the lecture notes, you'll find the link inside the description to the Calculus 1 playlist. Let's go. Wouldn't it be great to be able to travel at warp speed and go to another planet and another solar system? That would be so much fun. It would just be so cool, right? Star Wars and Star Trek combined, it would be awesome. Unfortunately, that's probably not possible, because Einstein proved in 1905 that there's a limit to how fast we can travel. So unfortunately, no warp speed. Now, where did this come from? This came from the equation that you see here in the center of your screen. This M stands for your mass, and M sub 0, called M naught, N-A-U-G-H-T, M naught. This represents your initial mass. And you can see in the denominator, it's being divided by a square root of 1 minus v squared over c squared. Now, c is the famous c from his theory relating energy and mass and the speed of light equals mc squared. C is the speed of light. So v is the velocity at which you are traveling. Now, we know from mathematics that we're going to have a problem here if v and c become the same value. If we were actually able to travel at the speed of light, this ratio would become 1, and we would have 1 minus 1, which is division by 0, which is not allowed in our numeric system. So what can we do? How do we figure out what your mass becomes as your velocity gets close to the speed of light? This is what's called a limit. The idea is I never actually get to where my velocity is the speed of light. I get close to it. And what does it look like it's going to be? And this is how Einstein discovered that it was not possible and there was no warp speed. So, what are some of the different things that led to the development of calculus? Let's take a look. So the limit is the first of the 3 major concepts that we study in calculus. We're going to be talking about the limit, the derivative, and the integral in this particular course. As we get further in our calculus series, into calculus 2 and calculus 3, we deal more with derivatives and integrals, but limits do still occur. And that's because limits are really the most versatile and the most powerful of the 3 constructs in calculus. Between the limit, the derivative, and the integral, the limit made it all possible. So the limit really is our foundational concept. So what is the idea of a limit? Well, let's suppose that we have some function and we're trying to figure out what the y value is when the x value gets really close to a number, like 2. So we've got 2.1, 2.01, 2.001. I'm getting really close to 2. What does it look like the graph is going to hit for the y value? If it looks like it's going to hit one single, finite, real number, then the limit exists. And it's that single, finite, real number. Now, it doesn't actually matter if the function is even defined at that point. It's what does it look like it's going to be, not what it actually is, which is kind of a blow your mind concept. Now, what happens if as you get closer and closer to that value, closer and closer to 2, maybe from the left and from the right, when you're getting closer and closer to 2, what if it hits one value up here and another value from the bottom? Well, then it's not the same number. It's not one single finite real number, in which case we say the limit, the two-sided limit, does not exist. Or maybe it's like an x squared graph, right? We got your old parabola here, and it just goes off to infinity. Infinity is not a number, it's a direction. It's like saying go west. Well, how far? Well, I didn't tell you. Go to infinity. Well, how far? Well, I didn't tell you, just keep going. So infinity is not a finite real number, so it can't be that the limit exists if it goes to infinity. But it is true, as x goes to the right, the graph of x squared goes up forever. So we'll say the limit is infinity, but technically that means the limit does not exist since it's not a finite real number. And we'll use the letters D and E to represent does not exist because we write them so often. And mathematicians are kind of notoriously lazy. If we write something a lot, we come up with a symbol or an abbreviation for it. Now, the mathematics behind this is pretty challenging, and it held up math, science, and engineering, and just about everything for centuries. Now, visualize, if you will, back in the 1300s and 1400s and 1500s and 1600s, they were struggling with a couple of different ideas, and they were unable to solve the engineering and mathematics problems and physics problems because they had these two problems. Problems were, how do you define the slope of a tangent line to a curve? So if you're looking at a curve, let's say that you've got some curve down here. So you've got a curve right here, and you want to look at this point right here, and you want to know what is the slope of the line that just barely touches it and skims along it. Well, they didn't know how to make that precise, right? They could guesstimate and estimate, but they couldn't get an exact answer without the limit. And the other question that calculus was created to solve was this idea of how much area is under this curve between x equal a and x equal b. Now, they knew how to approximate it, and they could get very close with their approximations, but they wanted the exact value. And for the exact value, they again needed the limit. Then in 1692, well, actually a little before that, Sir Isaac Newton in England developed the idea of the limit in calculus, but he didn't tell anybody until Gottfried Leibniz from Germany published his results with the same idea. And then Newton was like, hey, I got there first. Big brouhaha ensued, lasted about 100 years. Thank goodness for Leibniz, though, because Newton's notation was terrible. And we still use Leibniz's notation today. Here are the learning objectives we're going to cover. We're going to describe this tangent problem, slope with a tangent line, and how it led to the idea of this second major construct in calculus, the derivative. And then we're going to explain how the idea of the limit is involved in solving this, what's the slope of that tangent line problem. And then we're going to recognize that the tangent to a curve is actually the limit of secant lines as the points get closer and closer to the fixed point. Now, we're going to then identify instantaneous velocity as the limit of average velocity. Actually, this statement is exactly the same as the one above it, but in a physics realm. So an applied problem, but really it's the tangent problem in disguise. Then we're going to focus on the second major issue, which is the area problem. And it was solved by what's called the definite integral. The definition of the definite integral involves, you guessed it, the limit. The limit really is the most powerful. And then we're going to take a look at how the ideas of the limit, the derivative, and the integral led to different studies in infinite series and multivariable calculus, led to the Industrial Revolution, the disbursement of vast ideas, and the explosion of science as we know it today. Let's take a look now at the development of calculus. We've got our two problems, the tangent problem and the area problem. Now, the instantaneous velocity problem is really the tangent problem. So they're really basically two. So we're going to start by looking at the tangent problem. Now, when you look at a line and you talk about the slope of a line, we usually memorize this as rise over run or something to that effect. The change in the y values with respect to the change in the x values. This is actually called a rate of change. So rate of change is a super important concept in calculus and will come up over and over again throughout our study of calculus. A rate of change represents how one variable is changing with respect to the change in the other. And this idea, if you can get it at a single point in time or a single moment, that becomes the definition of the derivative. Now we want to look at these graphs down here and we want to describe their rates of change. Now, when we're looking at the rates of change, let's center these a little bit more. So on the far left, we have the graph of y equal negative 2x minus 3, which is a downward sloping line, all right, decreasing line. Now, how do I know it's decreasing? I don't know about you, but when I was learning mathematics, no one ever told me how to read the graph. So let me tell you, you read it from the left to the right. So from the left to the right, if it goes downhill, it's decreasing. From the left to the right, if it goes uphill, it's increasing. And from the left to the right, if it stays the same, it's constant. And this refers to the rate of change, which in all three cases is the slope of the actual line. So when we're looking at this one, we can tell that the slope is coming down 2 units on the y. For every positive 1 unit, it moves to the right. So we're going down 2, right 1, which gives us a slope of negative 2, which of course you can see from the equation right there, negative 2x minus 3 in slope-intercept form. And when we're looking at the next graph, of course, we have an upward sloping line or an increasing function. And when we look at this one, we see that it goes up 1, right 2. Up and right being the positive directions, this one has a slope of 1/2. And then we come to the constant function, which again just means that the y value is constantly 2, x is varying, but y is staying the same. So there's no change in the y value. So when you think about your slope formula, and remember your slope formula is y2 minus y1 over x2 minus x1, or you can think it as the change in y over the change in x. That's the Greek letter delta, the uppercase letter for D in the Greek language. And this represents the change. So the change in y over the change in x. When we're looking at this one right here, x is changing as we move across, but y is not, which means that the slope, of course, is 0. Now, what happens if we think about a different graph? And this time we want to take a look at the graph of y equals x squared. So let's scroll down and look at the graph right here. Now, if I start on the left and I want to look at the rate of change of y with respect to x, I'm really talking about the slope of the tangent line. So if I take this tangent line up here, I can see, that's my best effort at tangent. You can see right here that it is very steep and negatively sloped, decreasing, right? Left to right, it's coming down. So this means it must have some high value, but negative in sign. So negative 10, negative 12, who knows what it is. And then as x gets closer to 0, so I'm moving the x this way, and the y is decreasing because I have a decreasing function on this side. And this one is still steep, but not quite as steep. And then this one is less steep, and this is a lot less steep. And then when it gets really close, it's a lot less steep. And you can tell that the number, absolute value, is decreasing. It's still negative, but because it's negative, that actually means it's increasing. But in this case, the numbers are coming down in value. So like negative 10, negative 8, negative 4, maybe negative 1/2, something like that. And then for 1 instant, one instant only, over here, right at 0, it goes horizontal. And it has a slope of 0. Now, that's going to be a very important point for us when we get into chapter 4 and we're studying the shapes of graphs. This is what's called a relative minimum. And in fact, it's the absolute minimum of this graph. No other y value is as low as that one. You know that about parabolas. The vertex is either the highest or the lowest point. Then what happens to the slope as I move over to the right side? As I move over to the right side, notice that it again starts out not very steep, but now positively sloped. And then it gets steeper, and then it gets steeper. So the problem here is that it's not constant. The slopes of these lines are all different, which means that the rate of change depends on where the x value is. So if the rate of change is depending on x, we want some kind of formula to represent this rate of change no matter where I am. And that requires the limit and becomes, in fact, the derivative. Now we can approximate the rate of change of a function at a particular point by taking the slope of what's called the secant line. Now a secant line cuts through the graph. When you think of sect, S-E-C-T, think of something that cuts through. So an intersection, one road cuts across another. Dissect, you're cutting things up. You're in sections of a class. They took everyone in Calculus 1 and divided them into different classes. So S-E-C-T means cutting, or S-E-C means cutting. So the secant line, as you can see right here, this orange line, is cutting across the blue curve, all right? So we have two x values of interest here, a, which is a fixed point that we're not going to move, and x, which is not fixed, we can move it. Now, I can approximate what the slope of the tangent line is at a by instead taking the slope of the secant line. And to do that, I will use an m sub SEC. So when I write that out, it also looks like this, and it represents the slope of the secant line. And the formula is what you expect, y2 minus y1 over x2 minus x1, with which one being 1 and 2 not mattering. So we have y2 minus y1 over x2 minus x1. But in this case, we're going to say this becomes f of x minus f of a divided by x minus a. Now, this will give me the slope of the orange line that you see right here. Okay? Now, the idea is, what if I took a point that was closer to a? Would I get something with a slope that is closer to the slope of the tangent line at a? And the answer is yes. The closer you get to a, the closer the slope of the secant line will match the slope of the tangent line at the point. And that getting closer is the limit, right? So we're going to be studying limits to find the slope of the tangent line. Now, if you look at this graph, you can see that we did take another point closer to A. And notice, compare the lines here. We have this orange line, and then we have this teal colored line. Not a great choice of colors, but anyway. So let's call this one x2, f of x2. We'll call this one x1, f of x1. So this is our slope here. So when I'm looking at the slope of the line through these 2 points, I'll get a certain value for the slope of the secant line cutting through. And when I take the slope of the line connecting these 2 points, I get a different slope. And the idea is I want to take points that get closer and closer and closer to A, but I may not ever get to A because maybe it's not defined at A. Right? It is possible it's not even defined there, or maybe it's defined off somewhere else. And what I'm trying to approximate is the slope of the tangent line, which is right there. So as this x value gets close to A, the slope of the secant line approaches the slope of the tangent line. And we would write that the slope of the tangent line is equal to the limit, and that's my scrawl, as x gets close to a, of the slope of the secant line. So LIM stands for limit. And when we handwrite it, we tend to write it in cursive, but I know that most students these days don't even learn cursive, so just print it. But at any rate, make sure you put LIM. Now this means that I want to find the value as x gets infinitesimally close to a of the difference quotient. You may remember this is called the difference quotient from pre-calculus or college algebra when you're looking at that. And this right here, believe it or not, this slope of the tangent line, meet the derivative. This is the derivative. So the derivative by definition is a limit. Like I said, the limit is the most powerful of all three constructs. You can't have a derivative or an integral without a limit. The limit starts it all. Let's take a look now at some others. Oh, I should probably tell you how we write the derivative. So we use what's called prime notation. So my function here is f, and I'll use a prime up there, and this is the derivative. All right, so this is read f prime of x. Remember, this is notation, function notation. There's no multiplication here. This just means I'm going to use the variable x as opposed to t or p or q or something like that. I'm going to use x in the derivative function. So this is a prime. It's a slanted apostrophe mark. And this represents the derivative. Let's now take a look at a couple of examples. Right? And here you can see the actual tangent line graphed, right? So this is the tangent line here, and these are the other two lines where the slope of the secant line was getting closer and closer to the slope of the tangent line. All right. There is an interactive applet that you can play with on mathinsight.org. So if you want to, go ahead and Google Math Insight secant line, and you should be able to find it. Let's take a look at that now. So you can see here in Math Insight's applet window, the secant line to a parabola. So we have a parabola here in green, and we have a fixed point here, which is A, and you can see up here, it's allowing you to choose your X naught and Y, or X naught and X1. And that's gonna be these points here. You can also drag them if you want. You can just click on one of them and you can drag the whole thing. Now, what's happening is they're going to compute the slope of the secant line cutting through. So they take the change in y, which is the initial value, which is here at x naught, which is our a, plus scooch over a little bit, delta x, a change in x. So this delta x plus x naught is the same as our x, right? And then we want to subtract the value at the left endpoint from it. That's y2 minus y1. And then we're going to divide by the change in the x values, right? This is our slope formula right here. Watch what happens to this number right here as I scroll down. You can see that it's decreasing 1.6, 1.49, coming closer and closer and closer and closer, and we have a problem right there. This is what held up mathematics for so long. What do you do when there's no change in x? You cannot divide by 0. Thou shalt not divide by 0, cardinal rule of our system of mathematics. So what do we get? I mean, what did it look like it was going to be? This is the idea of the limit. And now we can click on show the limit, and you can see that at this particular point right here, it looks like the slope of that line is 0.944. This is the limit value. It approached one single value. And again, we can do this from the left or from the right. So I can take this up here and I can move this over here, and you can see as I'm getting close, from both sides, it will approach the same value, right? This is the idea of the tangent line problem and the solution to it, the limit. Let's go back to our notes now. Let's now take a look at example 1. In example 1, we want to estimate the slope of the tangent line at the actual point where there's no change in x by instead finding the slope of the secant line through the point 1, 1, which is where I really want to know what the slope of the tangent line is. This is my A here, x equal 1. And the point 5, 4, 25/16, which is also on the graph of y equal x squared. Now, 5, 4 is close to 1, but it's not super close. So this approximation won't be super accurate, but it'll be somewhat accurate. Let's figure out how to do that. First, we write the formula for slope of the secant line. M slope equals f of x minus f of a divided by x minus a. Now, my a value is the x coordinate of the point where I want to know what the slope of the tangent line is, and that's at 1, 1, all right? So I'm trying to evaluate it at x equal 1. So a becomes 1. Now, my function is x squared, which means that when I square 1, I still get 1. So f of a is equal to 1. Now, the next point I want to consider is x, which has been moved over a little bit from a, which becomes 5, 4. So I have x equal 5, 4, and then I need to find the function value at 5, 4. And when I square it, I get 25/16. If I plug these values into the difference quotient, substitute them, I get 25/16 minus 1, all divided by 5, 4 minus 1. Now we can go ahead and simplify this. 1 can be written as 16/16. So this is going to give me the following. Give me 9/16 in the numerator. In the denominator, I can rewrite 1 as 4, 4. That's an equivalent form. And this becomes 1, 4. Remember how you divide fractions? You multiply by the reciprocal of the denominator fraction, or as I like to say, the bottom of the bottom is the top. If you haven't heard this rule before, the top of the top is on top and the bottom of the bottom is on top, but the bottom of the top and the top of the bottom are on bottom. In other words, that rule simply becomes 9 times 4 divided by 16 times 1. The very extremes of the complex fraction end up in the numerator, and the inside parts end up in the denominator. So I can reduce this before I multiply, and this is going to give me 9/4, or roughly 2.25, right? Not roughly, exactly. Okay, let's take a look now at the next set of examples. In the next set of examples, we're again going to use the function x squared. And what we want to do is we want to fill out this table and find out what the value of the slope of the tangent line is at 1 more precisely by taking values that are much closer to 1. So 1.1, 1.01, 1.001, and I believe the next one is 1.0001. So what we need to do then is we need to compute these values and put them into our table. Remember that our function named f is y equals x squared. So now go ahead and pause the video while you fill out this table. Remember the y value, we'll work through one row together. The y value is basically taking the 1.1 and squaring it. So this becomes 1.21. And this, of course, is the ordered pair 1.1, 1.21. And then I want to take the difference between the function value and the value at A. A again was 1. So A equals 1 and f of A equals 1. So this is the ordered pair 1, 1. So the change in the y values is what we're representing right here, change in the y values. And this is going to give me 1.21 minus 1, which equals 0.21. Now, what's the change in my x value? Well, that would be the 1.1 minus 1. So this is going to be 1, oops, I forgot my point. 1.1 minus 1, which equals 0.1. And then we want to compute the slope of the secant line connecting those 2 points, 1, 1, and 1.1, 1.21. In that case, we take the change in y and we divide by the change in x. And when I take 0.21 and I divide by 0.1, I get 2.1. Did I lose something? I did lose something. What did I lose? No, that looks right. Okay. All right. So now you're ready. Pause the video, fill out the table, then turn the video back on and we'll finish the problem. So let's compare our values. You may want to pause the video again to compare yours to mine. I ended up having to add some rows so that I wouldn't get mixed up because this ordered pair got pretty large down here. When I found the slope with a secant line, I found that it started at 2.1 as we discovered, then it went to 2.01, then 2.001, then 2.0001. As we can see, it is getting closer and closer to the value of 2. If you were to do this again with an even closer value, what do you predict that it is eventually going to reach? If we could actually get there, which we don't. The limit never actually gets to the point, it just gets infinitesimally close. Well, the answer is, I think that the slope of the tangent line right there is going to equal the number 2, all right? So I think that the line is going to be going through the 0.11 with slope of 2. So when I look at this next example, 4, it wants us to go ahead and graph our function. So now I'm not great at graphing, so you'll have to cut me a lot of slack here. So I'm going to draw, looks like my scale is 1 to 1. So I'm drawing x squared, which is right here, and maybe one more out here. Do my best to connect smoothly. Ooh, that wasn't very smooth. And then it's coming up like this. Now, at the point 1, 1, which is right here, the question is, what does the tangent line look like? We said that it has, we think, a slope of 2. That's what it looks like it hits. So from this point, I'm going to go up 2 and right 1. And then I'm going to go down to left 1. And then I'm going to take a straight edge, which is around here somewhere, yield index card or driver's license, whatever you have available. And then we're going to go ahead and try to draw as close to a straight line as we can, going through those points. Now, mine's moved over a little bit. Let me see if I can try that again. Get it a little more on the actual point. There we go. And it does, in fact, look like this is accurate. This is close to, in fact, it is exactly the slope of the tangent line at the point 1, 1. Now, the slope of the tangent line up here at 3, 9 would be different because the rate of change on a parabola is changing at every point that we consider. Let's now take a look at the instantaneous velocity problem and why this is really, in essence, the same as the tangent line problem. When we think about instantaneous velocity, we know if we're traveling down the highway and we go, what did I say, 140 miles for 2 hours, we know from that formula that basically says distance is equal to rate times time, that we can find the rate by dividing the total distance by the total time. This gives you your average rate or speed, right? Your average velocity. So we would take the 140 divided by 2 hours, and that would tell us that we're going an average of 70 miles per hour. But what are you doing exactly 1 hour, 2 minutes, and 32.8 seconds into your trip? What is your speed at that moment in time? Well, the problem is when you're looking at this formula up here, the change in distance divided by the change in time. Well, if I'm talking about 1 instant in time, what's the change in time? Yeah, it's a problem. It's 0. Now, this baffled physicists and scientists for a long time, and they couldn't come up with a way to get around it, to get the exact velocity of something until Newton and Leibniz came up with the idea of the limit. So let's see why this is actually that tangent line problem in disguise. If we let s of t represent the position of the function at a point in time, so s of a is how far it has traveled at a time period, and s of t is how far it's traveled at t amount of time, then the velocity, the average velocity or speed, can be found by the change in position over the change in time. Well, that looks like the slope of the secant line, and it is the slope of the secant line. This is just the difference quotient written with a position function instead of a generic function named f. So when we're looking at this, to get the instantaneous velocity, we need to allow t to get arbitrarily close to a, closer and closer, but we can't actually compute it at a because there's 0 change in time at that point. So we find in this case that the instantaneous velocity becomes the limit as t approaches a of the average velocity, which again is just the difference quotient. Now let's take a look at example 5. Suppose we have an object moving along a coordinate axis, meaning it's just moving in a line, all right? So that its position at time t is given by s of t equals t cubed. Now, the object is not traveling in the shape of t cubed, which is, John Travolta's Saturday Night Fever. I know you guys were never born back then. I'm not even sure I was. So when we're talking about it, this is not what the point is doing. The point instead is moving along this line, but its position at any point is given by the y value on the function t cubed. And we want to estimate the instantaneous velocity at t equal 2 by computing the average velocity over a very tiny time interval. Now, you've had some experience with this, pause the video, work it out, and then turn it back on and we'll compare our answers. Okay, let's take a look and see how you did. Remember that we want to find the difference quotient to find the slope of the secant line, which is the average velocity. It's the same problem. So we're going to take s of 2.001, which is that value cubed, and subtract from it s of 2, which is 2 cubed, or 8. When you work out that value, you get something approximately this much. I put ... to indicate it continues. Do not ever round off at this point. You may never round off in the middle of a problem. You may round off at 1 point and 1 point only at the bitter end. You need to learn to use the store and recall button on your calculator so that you can keep as much of the significant digits as you can as you compute your values. Then divide this number, still in your calculator, by 0.001, and you'll get a value of approximately that much. Let's now talk about the second major problem that led to the development of calculus, which is how much area is under a curve between the curve and the x-axis between x equal a and x equal b. So when we're looking at this and we want to estimate the area under here, we can estimate it using geometry. Now, there are a lot of different ways that we could do that. We could divide it into ever smaller regions of maybe rectangles and triangles and all different kinds of shapes. What was discovered was that one of the best ways to do it was to use a series of rectangles. And you can see here, this is called a Riemann sum, which we'll be studying at the beginning of chapter 5 when we begin our study of integrals. So when we're looking at this one right here, you can see we've taken the same curve and we've divided the region between A and B into equal partitions. Partitions mean cut it up, basically. And each little one, they don't actually have to be the same length. They can be different lengths as long as the widest one eventually approaches 0. That's what we're going to do. So one of these right here, so even though they don't have to be the same width, from a practical standpoint, it makes our life easier if they are the same width. So we often make them the same width. This is delta x right here. I don't know where that dot came from. That off. All right. So when we're looking at it, we have delta x. Okay. Now, how can I approximate this area under the curve with these rectangles? Well, the area of a rectangle is length times width. And notice that the width of every rectangle is the same value. It's delta x. And what is the height? Well, the height here is the height at the midpoint. So it's actually the function value at that point. So I'm going to take the function value here and multiply by delta x to get the area of the first rectangle. And then I'll take f of x at this point and multiply by delta x to get the area of that rectangle. Now, this was known for a long time, actually millennia. This was known for millennia. But the problem was, how can you get the exact area? I mean, you can take more and more rectangles that are skinnier and skinnier and get closer and closer, but you can't get to the true, actual, exact answer without a limit. And that's what we did. We're going to take basically the delta x, oops, I erased and wrote at the same time, which is the width of each box, times the heights of the boxes, x1, x2. If you distribute it, each one will give you the height of that particular box. Right? Say I have n boxes. I take the height of the box times the width of the box. That's the area of that box. And then I'm going to add all that together, and that should approximate the area. But to get the exact value, we take the limit as either delta x goes to 0, the width of the boxes goes to 0. Now, A and B are fixed. They can't change. If A is 2 and B is 5, then that's always 2 to 5. But if delta x gets smaller and smaller, I must have more boxes. So you'll see this limit written two different ways. As the number of boxes goes to infinity, or the width of each box goes to 0. The limit of that becomes the exact area under the curve. All right, let's take a look at an example. This, of course, is what is called integral calculus. Riemann sums are the very beginning of integral calculus. Now, without Newton and Leibniz coming up with the idea, the concept of the limit, this integration problem, this area problem would not have been solved. It was not solved immediately. It took some time. All right, so when we're looking at this one right here, we want to approximate the area under the curve of x squared plus 1 between 0 and 3. So A is going to be 0, and B is going to be 3. Now, how wide are each of my boxes? Well, I'm going from 0 to 3, so the width of my interval is 3 minus 0. And I have 3 boxes, so the change in width of each box is going to be 1. And again, they don't have to be the same, but we usually choose that to make it easier to compute. And then we want to look here. This one is what's called a right Riemann sum, where we're taking the right endpoint for the height of the box. The one we saw previously was a midpoint Riemann sum, where we were taking the midpoint of the rectangle as the height of the box. There's also a left Riemann sum. So when we're looking at this one, the height right here is 2. So I'm going to take my height, which is 2, and I'm going to multiply it by the width, which is 1. Okay, got to catch up in my notes. So I've got height 2 times 1. This is f of 1 times delta x plus f of 2 times delta x, which is going to be, again, delta x is still 1, but f of 2, I've got to count it out over here, like 1, 2, 3, 4, 5, right? So I have 5 times 1 plus, and I've got to squeeze this one in here, f at 3 times delta x. And at 3, it looks like it's at, let's see, this is 5, 6, 7, 8, 9, 10. It's up here at 10. So I've got 10 times 1. And then I add these together, and the area under that curve is going to be approximated by 2 plus 5 plus 10, which is about 17 square units. Now, keep in mind that what I'm really finding, oops, that's a little wide, is this area right here. This is what I'm approximating, is this area here that I've now shaded in purple. Right? I'm approximating that with the area of the rectangles. And because the rectangles all stick up above, I've overestimated the area. So I know it's actually got to be probably below 17. Okay. Now, how does multivariable calculus come into this? In our discussions today, we've only looked at the change in a single variable, y, with respect to the change in another single variable, x. This is called single variable calculus. But we live in a three-dimensional world. All the graphs we looked at today were two-dimensional, but because we live in a three-dimensional world, we have to be able to describe it. So calculus can be expanded into multiple dimensions. In 3 dimensions, that's the space we live in, but you could also add a 4th, which could be time or something else. And we can compare the position of an article, some particle with respect to x, y, and z at a point in time, right? So the change in position with respect to time. And we can still employ the techniques that we'll learn this semester in order to solve those kinds of problems. I hope you'll join me for the next video where we introduce formally the notation for the limit and begin talking about, from a graphical sense, what the limit is. See you there.